Our next speaker is Creties Jenkins, who is a partner of Rose Subsurface Assessment. Creties is a geological engineer with Rose Subsurface Assessment, and he has over 35 years of global experiences in petroleum exploration, appraisal, and development. The topic of his talk is quantifying and reducing subsurface risk in carbon dioxide storage projects. Thank you.
Well, thank you very much for the introduction. I always get suspicious when people's biographies are longer than their abstracts, so I'm glad mine wasn't in this case. I'm here to talk a little bit about reducing subsurface risk in CO2 storage projects this afternoon. And I want to first of all thank my colleagues, Pete Carragher, Peter Pessman, and Rosalie Constable for their contributions to this presentation. As the French philosopher Voltaire was famous for saying, if you wish to speak with me, define your terms, so let's do that. If we're going to talk about risk, then we're going to, hello, who's your buddy? There we go. Risk is exposure to danger, harm, or loss. And we generally think of risk in terms of financial loss, but there's also environmental safety and reputational losses, right? Think Macondo, where 11 people perished, there was tremendous environmental damage, and the cost to BP was about $60 billion. Uncertainty is the range of possible outcomes, and we must identify all of the impactful uncertainties. Those are the factors that control that range of uncertainty. Chance is the probability of a given event, and we'll be speaking this afternoon about the chance of geologic discovery, development, and commerciality. An event we'll define as an unfavorable occurrence. It can be linked to some underlying cause, or at least we will try to do so. And then failure is a project outcome from foreseen or unforeseen events that result in significant losses and require substantial corrections or project cessation. So keep those in mind, if you will, as we walk through the presentation here today. While CO2 storage is relatively new, the process of storing injected fluids underground is not. And natural gas storage began more than a century ago to meet our winter heating needs, and then water injection began in the 1930s to dispose of produced water. And then we started water flooding in the 1940s and 50s, and by the time we get to the 60s and 70s, we're injecting CO2 for enhanced oil recovery. The history of those injection operations provide considerable insights into the types and frequencies of failure incidents. And while most are facility or wellbore related, there are a small but significant number that have to do with geological failures, generally on the order of 5% or so. And CO2 storage is susceptible to these same sorts of failures. And as we heard in the last panel session, so is hydrogen. In fact, perhaps even more so because it's less dense, less viscous, and a smaller molecular size than CO2. And just to give us a sense of what sorts of mechanisms might be responsible for CO2 leakage, let's have a look at this diagram. You can see on the left-hand side there's a well with a red bar that goes down to the bottom, and that well penetrates limestone at the base, that's in blue, and yellow sandstone above that. And as we inject the CO2, what we find in that limestone is that the limestone grades into impermeable anhydrite to the right, and so that makes the reservoir much smaller than they thought it would be, and so it pressures up, creates fractures which breach the seal, and then that gas also moves down the faults and creates seismicity, earthquakes. In the sandstone where the gas is being generated, or CO2 if it's supercritical, that CO2 can move through the sands and up the fractures. It could also move into more permeable pathways. It could move into old well bores and find its way to the surface. And it may not come all the way to the surface. It may exit in shallow groundwater aquifers. So this is a nice little diagram that shows us some of these pathways of CO2 leakage that we need to consider. When we think about risking these projects, these subsurface projects, for the chance that you'll have leakage in these different ways, we like to reference the Storage Resources Management System, which is commonly used and was developed by the Society of Petroleum Engineers along with some sister societies. And in the SRMS, we define the chance of discovery as the chance of encountering significant storable quantities in which we can put the CO2. The chance of development is the chance that those storable quantities will be commercially stored after discovery. And the product of those two is what we refer to as the chance of commerciality, using terminology from the SRMS. And if we want to estimate P sub G, the chance of discovery, and P sub D, the chance of development, we can do so with independent chance factors. So P sub G can be estimated by considering reservoir, injectivity, containment, and trap. And you can see the key characteristics that we're looking to quantify when we do so. For each of those independent chance factors, we'll look at the subcomponents, we'll assign a value of between 0 and 1 to each of those, and then the product of those becomes P sub G. So if we thought there was a 90% chance of each of those four, we would multiply those together, and we would have a P sub G of 66%. Similarly, we will do something like that for the chance of development success. And again, this would be applied after you have the discovery. There's the chance that your plan is going to be technically mature and executable and such, that you're going to be able to inject longer term at rates that can put away the contracted volume, and that your facilities are in place and that you are in compliance. And again, we assign values of 0 to 1 to each of these, multiply them together, and the product becomes P sub D. And in addition to thinking about P sub G and P sub D in this way, which is consistent with the storage resources management system, we can think about P sub G and P sub D in terms of current and future risks. So for P sub G, we would call that a current risk because we can go out there and we can quantify whether or not we have a discovery by drilling a well. We'll log the well, we'll take some core, we'll do an injectivity test, and if we're able to convince ourselves that we then have the potential for commercial success, we can go ahead and inject longer term, see if we can store those quantities that we have contracted, and then also ensure over time that we can maintain the ability to inject through following regulatory rules and having a social contract with the public. You can see that there are 4 different stages here, as indicated on the decision tree, and between each of those stages we have stage gates. And the stage gates are illustrated by the black squares with the yellow circles. Those are decision and chance nodes because at each point along the way here, you're making a decision whether you want to spend more money and continue with the project or whether you want to exit or at least park it for some period. And the reason that it's important to use a staged approach like this is because as you move from the lower to the higher parts of the decision tree, you are incurring greater capital risk. You spend a little money at first to understand whether you might have storable quantities, and then you spend a lot of money getting the CO2 to the project and injecting it into the ground. And by putting those stage gates in there, we can be much better stewards of our stakeholder capital by spending it in a responsible way. And that's why we set things up this way. Now, to talk a little bit more about these current and future risks, let's look at some examples here of current risks under each of these subcomponents. Reservoir risk, for example, might be that your thickness isn't sufficient or that your pore volume is smaller than expected. Your injectivity means that you're unable to attain a sufficient injection rate, or perhaps your pressure and temperature are too low for the supercritical conditions you need to store the contracted mass. You want sufficient containment, which means top seals, lateral and base seals that exhibit capacity, integrity, and continuity. And then finally, if you have a trap, you need to understand what the size of the trap is, whether it's big enough, and whether you have compartmentalization within the trap. So these are some examples of these independent chance factors that we would have to think about when risking this for P sub G. And an example of a project that actually failed to get past the current risk stage, we could consider the ZeroGen project in Australia, where, as you can see here, they had at least 4 tests of the interval of interest. And each of those tests have a KH value, that's permeability thickness, which is a proxy for injectivity, that were somewhere between about 6 and 30% of what was estimated from core plugs. So that's too low to have a chance of commercial success. And therefore, this project fails, piece of G is not won, and you exit from the project. If we talk about examples of future risks, so this is the chance of development, for our plan, the inability to contract sufficient volumes or difficulties in permitting and building the transport pipelines would mean that you have a failure of the plan. For the injection component here, induced seismicity could cause a cessation of injection, and you may not have sufficient volume to actually store that CO2 that you inject. For the facilities, you may not be able to supply that steady and sufficient volume of CO2 that you need at the contracted rate. And in terms of compliance, perhaps you have leakage or the plume migrates somewhere it's not supposed to, changing the public perception and causing the regulators to pull your permit. So these are the sorts of things we worry about after we have a geologic success and we're trying to assess the chance of development. And just to give you an example of how future risks may be identified and mitigated, we could look at the Snøhvit project in the North Sea, where the reservoir that they chose, the Tuborn Formation, they thought could possibly pressure up in the early stages of the project because it contained discontinuous sands. And sure enough, if you look at that graph on the left, you can see the blue curve creeping upwards at higher and higher pressures over time. And what you don't want is for that red curve to intersect the red line that says fracture pressure, because if that happens, then you have breached your seal. So as it got close to the red line there, they recompleted the well into the overlying Stowe Reservoir, which had previously been identified as a backup zone, successfully recompleted it, decreased the bottom hole pressure, and the project was successful and could continue with development. And it was successful due to built-in optionality. And that's an important term to understand because we want in our projects to have optionality, things that we can do if we have potential for failure. And this is a good example of that. So that's a little bit about current and future risks, and you can see where they fall in a plot like this of project risk on the y-axis versus time and project stage on the x. So that line that you see between current risks and future risks, that vertical line, the zero-gen project would fall to the left of that line. That's where it failed. And that failure was a primary risk to the operator because not much CO2 had been injected into the ground. And so the onus is on the operator to abandon the well and pay for that. When we get into the future risks, as you just saw, the Snøhvit project had a recompletion in the early stage, so it encountered a peak risk in shortly after the geologic discovery. And then if we continued to inject in our projects until we put all that CO2 away, which might be 30 or 40 years, your peak risk may be where that red dot is. So that's very commonly where the greatest risk is, because that is the point at which you've pressured up the reservoir the most, and then risk begins to decrease after that as the pressure dissipates. But during that period, it is possible for that CO2 to migrate somewhere it's not supposed to. So there could be a peak risk later on in the project past the point at which you finish injecting. So this points to the fact that we have various times along the project length in which we may have these different peak risks, and we need to be able to identify them, anticipate them, and mitigate against them. And that's what we're going to talk about now. We're going to talk about a couple of the ways we can reduce risk. I have a list here we'll go through very quickly. These are some of the ways in our company we try to help clients reduce risk. And those include framing sessions where we can identify key uncertainties, risks, and mitigation options. Quantifying the value of information we need to gather to understand these reservoirs. Building a library of analogs, including proposed projects for which a lot of data may have been obtained. Building models of sufficient complexity to assess risks and actually running failure cases so that we understand under what circumstances the project could fail. Using the staged approach, which I talked about a few minutes ago. Determining that range of possible outcomes and keeping your ranges wide, particularly if you don't have a lot of information. Effectively communicating your intentions and keeping everyone on board. Recognizing and mitigating your biases. As human beings, We are plagued by bias, particularly things like overconfidence, which cause us to narrow the range of possible outcomes, and overoptimism, which causes us to choose a high value within that narrow range. And then there's also other biases, including the confirmation bias, where we collect and interpret data in a way that confirms our beliefs, or the motivational bias, which leads us to act in ways based on our personal desire for a given outcome. And then we can implement assurance processes to provide independent and consistent guidance, and these often consist of peer assists or peer reviews to make sure that there is technical rigor involved in the assessment. And finally, we'll quantify and document those expectations so that we can conduct some performance lookbacks. And it is also very helpful to use a risking tool to guide your assessment. That's the last thing I want to talk a little bit about today, is a risking tool and how you might be able to use that. There's several steps here that might be involved in a risking tool. First of all, you want to define a list of potential events that could occur for your project and decide on the time frames that you want to use. And generally those are tied to the project stages. So we have the early stage injection, and then 5 to 45 years, during which you might have the peak pressure that you'll see in the reservoir. And then after project closure, you have a period up to perhaps 100 or even 1,000 years in which you need to be considering monitoring of the project. And then you'll build some ranges of financial impacts, as you can see in the table there to the right. We've got values of P90 and P10. So P90 means there would be a 90% chance that your incidental event would exceed a cost of $0.5 million, and only a 10% chance it would exceed $5 million. And then you'll evaluate each event to try to estimate the annual chance of failure in a given time frame and the financial impact of that failure. So this is how you set the project up, by answering various questions and applying these financial impacts to those particular chances of failure, and then you aggregate the events using Monte Carlo simulation. And you conduct enough sufficient trials in order to sample the rare events. Because remember, if you look at the scale at the bottom, we would say something is extremely rare if it only has a 1% chance of occurring on an annual basis. But if you're responsible for keeping that CO2 in the ground for 100 years, and there's a 1% chance it will fail each year, you're virtually guaranteed a failure within 100 years. And that's the point of applying this sort of process, because we're dealing with much longer time frames in terms of storing CO2 than we do with some of our other processes in terms of underground storage. So after you set this up, then what you can do is create a plot like this, which has likelihood on the y-axis and time on the x-axis. The blue curve that you see is the chance of 0 events over time. And you can see that chance of 0 events reaches a value of about 60% per year during the time in which you're injecting. And then 100 minus that blue curve gives you the green curve on the bottom. And that green curve is the chance of at least one event occurring in a given year. And the orange, gray, and yellow bars are the chances of 1, 2, and 3 events occurring in a given year. And of course, the orange bars are much longer because the chance of 1 event occurring is much greater than 2 events in a given year. And you can also see that at the end of injection, about year 25, the chance of these events drops considerably and becomes near 0 after 40 years. So what we're trying to do is understand what's the chance that these events potentially could occur that we've identified, what their frequency is, and then we have to think about what the cost might be associated with these. And that is determined on this graph here, which has annual risk in terms of millions of dollars undiscounted on the y-axis and time on the x-axis. So for example, where you see the green curve there, that's the mean outcome. That mean outcome tells us that on an annual basis, there's about a 40% chance that a $20 million event could occur in any year. And then as you move up from the green curve, there's a light blue curve there. That's the P10. That means there's a 10% chance that a $40 million event would occur in any given year during that project. And then we move to the red curve and the blue curve, which are the 1% and 0.1% chance of events, which is 1 in 1,000. And you look at those and say, well, the chance that those will occur is quite small. Those are what Nassim Taleb in his book might call the black swan events. but they can happen. You should recognize if they're possible and what their impacts could be. And you can see those sorts of events, which are very low probability but very high cost, could be in the $150 to $200 million range. So this is the idea, to try to give people a sense of when these events might occur, what might be the financial impact associated with them, so it is on their radar. And some of these you'll want to mitigate, others it's pretty difficult to mitigate for a 1 in 1,000 year event, but at least you should understand that it's possible. Okay, to summarize then, CO2 transport and storage are susceptible to multiple risks, as revealed by the history of subsurface injection projects. We can quantify them in PRMS, or SRMS rather, as PG and piece of D, and those become current risks and future risks in our risking model. Those current risks can be addressed today, the future risks addressed by longer-term injection. Those risks are not constant through project life, and they may peak at different times due to various factors. There are many ways to reduce risk, as I walked you through that list, and a risking tool like I showed you here can facilitate a quantitative understanding of risk over project life, including the number of events per year and their potential financial impact. And in quantifying risks, the adverse events can be foreseen and mitigated, or at least we hope so, which will minimize some of the financial exposure and hopefully maximize the chance of project success. And I'll close by saying those risk assessments need to be calibrated to analogous CO2 storage projects. We don't have very many of those as present, so the assessments will improve with time as more projects are implemented. So that's what I have for you this afternoon. I want to thank you, and if we have any time, I'll be glad to take questions. If we don't have time for questions, you can see my email address there. Please drop me an email if you would. I'd be glad to share what I know with you. Thank you so much. Is that a question?
We have time for one question.
Oh, Eric's got his hand up over here.
How do we get a hold on of your risking tool? Is it something you anticipate on licensing to people or solely working through ROSE?
We have already licensed it. The entity that's using it is the North Sea Transition Authority. It's the regulator in the North Sea for this. So they want to understand how this works and how they might be able to use it to help inform the risks of various projects. So if any of you would like a demonstration or would like to talk to us about it, please, again, just drop me an email. So thank you, Eric.